Hi everyone, my name is Jessica, and I'll be presenting on the detection of wheelchairs using laser scanning sensors under the category of mobile robotics. I'm first going to start with an overview of the problem and why it's important to solve. Mobile robots are becoming increasingly common in public spaces. For example, this is a sidewalk delivery robot that can make short-distance food deliveries. So how does a robot like this see its surroundings? What happens when there's a pedestrian in its path? This robot is equipped with onboard sensors, one being a laser scanner, which shoots a plane of lasers into the space in front of the robot. When objects interrupt the laser beams, the location of the interruptions are calculated and returned. From a bird's eye view, it looks like this. The points of interruption correspond to XY coordinates on the graph. There's fortunately a lot of established algorithms that can interpret this pattern of points and classify it as a person. So if the robot knows that it's in the path of a pedestrian, it may yield or perform some other interactions with the person. However, what happens when the pedestrian is a wheelchair user? The lasers will be interrupted at different locations, creating a more spread out scatter pattern. There are far fewer algorithms that could classify points as wheelchairs, so the robot may think that a wheelchair user is an unknown object and not know how to behave around it. In fact, last fall, the University of Pennsylvania rolled out a fleet of campus delivery robots. Unfortunately, this created an alarming safety issue when a wheelchair-using student was unable to clear the intersection safely because her path onto the sidewalk was blocked by one of these robots. This incident raised some attention in the media, bringing to light the dangers that people with disabilities face due to sidewalk robots. This raises the question, how can we make human-robot interactions with wheelchair users safer by making sure that robots can recognize wheelchairs with their onboard sensors? Now, I'll briefly talk about the literature background on wheelchair detection. Wheelchair users make up a significant portion of the population, and they already face higher injury risks in public. Wheelchair users also have different movement characteristics, so the robots cannot expect them to move in the same way as foot pedestrians. Previous studies have found that range data from laser scanners is a good way to detect and classify objects in real time. Existing wheelchair detection algorithms do not detect orientation, which is important for estimating the trajectory of the wheelchair, so the robot knows which direction it's moving in. Here, I'll explain the methodology behind detecting wheelchair orientations. To collect the data, I use a SICK LMS300 laser scanner mounted on board a PowerBot platform. Next, the data points are pre-processed in order to segment them into distinct objects. This is achieved using a clustering algorithm. After the list of objects have been identified, they would be passed into a two-stage classification algorithm. The first step classifies the object as A, a wheelchair, or B, not a wheelchair. If the object is identified as a wheelchair, it is further classified into one of the 6 listed orientation categories, which are front-facing, left and right 45-degree angled, back-facing, and left and right side-facing wheelchairs. Now I will discuss the results obtained at each step. This is what the live laser scanner data looks like. If you recall from before, this is a bird's eye view of the room, and the sensor is positioned at the bottom of the screen, like so. The gray outlines that I've added represent the walls, columns, or other irrelevant objects. The moving cluster points represent the wheelchair. So again, this is what the data looks like in real time. Now I want to segment out the objects from a raw frame of data. By applying distance and error thresholding, I create a line removal algorithm to remove points that fall on a continuous straight line. These points may represent walls or other lawn objects that do not belong to a wheelchair. With the remaining points, I pass them into a density-based clustering algorithm called dbScan, which removes outlier points as well as creates object clusters. The cluster representing the wheelchair in the green has been segmented out quite nicely, and I manually label it as a left-facing sideways wheelchair. The dot represents a calculated centroid of the wheelchair cluster. A list of about 10,000 objects that were segmented from the laser scanner data, 25% of which are wheelchairs, is passed into the binary classifier. The XY coordinates of the points in an object is casted into a 100 by 100 pixel image. This is to standardize the input format of the data. I experimentally tuned 4 different classifiers: a 2-layer neural network, a 2-layer convolutional neural network, a random forest with 300 decision trees, and an AdaBoost classifier with 100 trees. The results for classification time, training accuracy, and testing accuracy are shown in the table, and the ROC curves, which optimizes between true and false positives, are shown in the graph. We typically want fast times to mimic real-time conditions of the robot, and a similar training and testing score to prevent model overfitting. The neural network achieved a good balance between training and testing accuracy with a fair time. The convolutional neural network performed slightly better but was extremely slow. The random forest has high accuracy and low time but may be overfitted. The AdaBoost classifier was the least accurate. With a good trade-off between overfitting and time, we moved forwards with the neural network. The wheelchair objects are passed into a round of multi-class classification, where the outcomes predict one of 6 major orientations. This way, the robot will know which direction the wheelchair is facing to estimate its motion trajectory. I used another 2-layer neural network with L2 regularization, which achieved around 89% classification accuracy. The orientation classes are labeled 0 through 5, and the outputs of the classification algorithm is shown in the confusion matrix. This indicates how often each orientation was correctly classified, and which other orientations it was mistakenly classified as. The ROC curve for each class, as well as an aggregated micro and macro average, are shown on the right. We could see that front and back are often misclassified as each other. Left-facing 45-degree angle is often mistaken for front-facing, which may indicate bias in the data. Overall, the performance is acceptable for a multi-class classifier, but the accuracy could be improved. Finally, I'll give an overview of my research and talk about the next steps. My research is the first attempt in classifying wheelchair orientation, and I did this by using 2D laser scanner range data. The classification algorithm is in the process of being fine-tuned and analyzed, but the current version achieves a compounded accuracy of 85% with a 1.6 millisecond processing time per object. However, there were some significant limitations in the approach. The sensor had low resolution and lost object details over 4 meters away. The orientation of a wheelchair should be a continuous function, but I had to round them to the nearest category for the multi-class classifier. Segmentation sometimes merged together separate objects that were very close together. When collecting the data, since I was taking many static snapshots, the objects do not change from frame to frame, which duplicated input samples and possibly created bias in this data. Due to limitations in space, I could only record data in 2 rooms, so there's a lack of diversity in the environment. I split the next steps into 3 categories. For the data collection, the classifier should be tested with other existing datasets to eliminate bias. Collecting and labeling more data in different environments and introducing more motion will also help. A further step is to fuse the laser scanner data with that of a camera, which provides more scene details. The algorithm can be improved by looking at temporal features between consecutive frames to reinforce scene understanding. Wheelchair orientation can be discretized further or represented continuously to improve precision. Lastly, the algorithm should run in real time so the robot can react quickly. An extension to estimating the wheelchair's orientation and a location is state estimation, such as tracking the velocity of the wheelchair between frames. A Kalman filter can be applied in this case to predict the wheelchair trajectory and serve as an input to the robot's control algorithm. Now, thank you for listening to my virtual presentation. If you have any further questions or comments, you could reach me at my email. Last but not least, here are my list of references.